Engineering 305. This is example problem from Chapter 8, example problem number 1. This is a series of these problems where we're going to wind up doing a lot of algebra. This is the Algebra Olympics. I'm not sure of another area in your engineering education where you're going to do a lot more of the, just a straight math class I get, but within the engineering stuff, there's just a ton of algebra that we're going to do here. So let's dig in, and I don't want to say get it behind us, but it is kind of fun. It to me, I'm a geek, I get it, but I do enjoy this. And there are reasons why I enjoy it, because I can go check my answers, and so we'll see that with this example. So anyway, here we go. Example problem 1. A beam is loaded and supported as shown. It has a uniform load W over the entire top of the cantilever beam. So what they're looking for is the equation of the elastic curve. When they say that, as I'm helping, because of COVID and all of us are fighting different things, I'm helping my oldest with calculus, and so much of it is just understanding what the question is. That elastic curve that they're asking for is this v as a function of x, and I don't like this. I don't like the whole v, even though I'm going to use it in those equations. I'm going to show it, that v or that nu. I want to call it delta as a function of x. That's what they want us to find, and so that's the question that they're really asking for in A. Part B, find the deflection at the left end. I'll write that out. Find the deflection at 0. And lastly, the slope at the end of the beam. Find at the left end. Find theta at 0. Okay, so those are our goals. Find delta as a function of x, find delta at 0, and find theta at 0. And that's using their coordinate system, which are starting at the left end. So let's get into it. The first thing I'm going to solve is the sum of the forces in the y direction are equal to 0, are equal to, and my beam segment is going to look like this, and I'm going to cut it there, and at that point I'm going to put my shear and my moment on it. All right, and that has a distributed load. Are the sound effects too much? Is it okay? It's okay. Da 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 da. Okay, I can see that my microphone's working. I was going to pause it, but the force acting down, I have no reaction force, nothing going up. So the distributed force is a minus, I don't want black, minus W times whatever distance I have, x. That's all acting down. And then I have my minus VR, maybe I should label that VR and MR. And that's all I have. That's all I have. So VR is equal to minus W times x. Now, if I go to my equations, you can see that I can take my load equation and I can I can take my shear equation and I can integrate that once to get my moment equation. So I'm going to do, if I integrated that once, the integral of VR dx is equal to minus wx. Well, that's going to be equal to minus wx squared over 2 plus a constant. Okay, with me? Just take this, and we're going to put that on the side for right now. We'll just set that aside. I'm going to go to sum of the moments about the cut is equal to 0, is equal to, now this moment from this stuff is going to cause this to spin that way, so it's positive. So that's going to be a a W, and how much of it that I have is times X, and then the place where it's being pushed down, if this is X, this line of action is X over 2. And so I'm going to multiply that by X over 2. And then I don't have anything else, and I've got a plus MR equal to 0. So now I've got, and then I'm just going to rearrange that, and I've got MR is equal to minus WX squared over 2. Now, if I look at what I set aside here, I solved it here. So as if I want this to work out, I mean, in one sense, that C is equal to 0, and then this is all good. And I could solve it using, I've solved this essentially already 2 different ways. I looked at VR, and then I integrated to get to this point. Or I simply did this. This is other path. But I get to the same thing since C is equal to 0. Now, what does that mean? The moment, that just means there's no moment at, if I plugged in the moment at, the moments, if I evaluated, how do I evaluate, the question is, how do I evaluate C? Well, what are my moments at X equal to 0? So the moments at X equal to 0 are equal to 0. So that means when X is 0, this drops out and I get C. Well, that's equal to C. So I got to get rid of that for you to see that. But I like that. It's kind of good. We're doing the same thing. We've done it 2 ways. We get the same result. It's good. I like that. Let's keep going. I want to find out what slope is. Well, the derivative of the slope with respect to X is equal to the moment, or I can simply integrate the moment. And actually, I can't do that because that EI fit in there somewhere. Let's take a look at that equation. The moment equals EI times the slope. So if I put EI here times the slope, that's equal to EI d theta dx is equal to the moment. Right? Okay, so that means I have to integrate this. So I'm going to go EI, well, what you wind up getting is, and I didn't do this in lecture, and maybe I should have, but it's a simple rearranging. I'm gonna, it's not an equals, d theta dx is equal to the moments divided by EI. Then I'm just going to integrate both sides. So it's d theta is equal to mr over EI dx. Now I'm going to put an integral, one more step. I'm going to put an integral on both sides. All right, now that's going to wind up giving me theta is equal to 1 over EI comes out front, and then I've got an MR dx. All right, so before I slide that off the top of the page, MR is equal to that, so equals 1 over EI times the integral of minus W x squared over 2 dx. Is that hard? Oh my goodness. Somebody's got to yell at me. Besides me. Let's go back. EI d theta dx is equal to MR. Put that in. Then it's a d theta dx. That's, I just moved the EI over, right? And then I move the dx over, and I integrate both of those to come up with this. And now theta is equal to 1 over EI times minus W x cubed over 6 plus C. Now, for clarity, I might have wanted to call this C0 and I might have wanted to call this C1. Maybe not. Just depends. I'm going to call that C1 because we are going to get into other values of that. Namely, because I got to pull this back up. Remind me to put that back away when I'm done. The deflection is equal to the integral of the slope. So delta is equal to the integral. Can you tell the difference between a delta and an integral? Is equal to the integral of, I'm going to pull this out front because it's a constant still, minus wx cubed over 6 plus c1 dx equals, I just thinking I left my formulas up again, so 1 over EI minus W x to the 4th over 24 plus C1x plus C2. Now, there's my equation, and legitimately this is the equation for, that's what we were asked to find. We were asked to find the deflection as a function of x, and that's it. But to really do a good job, I need to evaluate C1 and C2 because it still could be anything. So we need to look at our situation, and let me pull that up. What are the boundary conditions that help us analyze this? Now, I already used one boundary condition, and that was I looked at this and said my moments at 0 are equal to 0. Did I do that? Oh, yeah, right here. So now I need two boundary conditions to help me evaluate C1 and C2. And unfortunately, these aren't necessarily as pretty as some of the other boundary conditions that we might have had. But it's okay. We'll get it. One boundary condition, if you look at the picture, is that I know that my deflections at L, that's all the way against the wall, right? That way. See, my picture's backwards. Anyway, all the way against the wall that way. I know the deflections at L are equal to 0. That is part of a cantilever beam. That defines that beginning point. The other thing about a cantilever beam, the slope at L is equal to 0. So now I have two boundary conditions, and I've got this equation I can pop those into. Delta at L is equal to 1 over EI times minus WL to the 4th over 24 plus C1 times L. I'm not wearing my watch, so I don't know why that happened. Plus C1L plus C2. That's all equal to 0. My EI goes away, right? Because I just, yep, get rid of that. And so then I've got C2 is equal to WL to the 4th over 24 minus C2L. C1L, sorry. Well, it's been a while since I've done these because I think most of you would have said, no, don't plug that one in. Don't do that. Solve for C1 first, because I can solve for that right up here. You're right. So theta at L is equal to 0 is equal to 1 over EI times minus WX cubed. Oh, it's not X. Minus WL cubed over 6 plus C1. Well, that has to be, this inside has to be equal to 0. So C1 is equal to WL cubed over 6. Well, now you can see I could plug that right in up there, equals WL to the 4th over 24 minus WL cubed over 6. That's C1. This is dropping in right there. And then, to be clear, I put the L out there. All right. So now I really want to simplify this, and if you look at that, this is 1/24, and that is actually going to be 4/24. So C2, I can do this. Just add width to my page. It doesn't work that way with normal homework. Equals minus 3/24. I don't want that at all. WL to the 4th. That's actually equal to minus an 1/8, right? WL to the 4th. All right, so I'm going to go all the way back here and write C2 is equal to minus an 1/8 WL to the 4th. Now, I should rewrite this equation with my constants plugged in, because that's the beauty of this. It's 1 over EI minus W x to the 4th over 24 plus C1. I got to go back and look. C1 is right here. C1 is WL. Oh my goodness, can't do that. WL cubed over 6 times X plus C2, which is I'm gonna erase that and put in a minus 1/8 WL to the 4th and close the parentheses, and that's my answer. Since that's a beautiful answer, I'm boxing that all in. Now, we could go right on to the next section. Oh, it got dark in here. It got dark outside. It's okay. We could go right on to the next section, but I don't want to. I'm going to pause, and I'm going to go grab... I want to, because here's the cool part, is we can validate this. We can look at this. This is a standard, that problem is a standard cantilever beam. And so I want to show you the answers that the book has and that we're going to use later, because this is a general case. And so I want us to look at that. So let me go get these equations. I'll pull them in, copy and paste them, and then maybe we'll go ooh and ah, and maybe we won't. Okay, actually I changed my mind, and that's because the two things that we're supposed to do yet are theta at 0 and delta at 0, and so I wanna take a second to do those before I go get the other thing, before I do the thing the other. Anyway, you can see. let's punch in delta at 0 is equal to 1 over EI times What's in brackets? Well, the first term goes away. The x is 0, so that goes away. The second term goes away, and I get a minus 1/8 WL to the 4th. That's I should have my brackets match up. How much do you erase? WL to the 4th. All right. Or I write that as minus WL to the 4th over 8EI. Because that's the way it's going to show up. And then last, the other part is theta of 0 is equal to, and here I didn't write out the equation explicitly, but theta at 0 is equal to, well, that term goes away, so it's 1 over EI times C1. Okay? See that? It's 1 over EI times C1. I'm working right there. So I'm going to write that 1 over EI times C1. Now I got to go back and find, oh, look at that. C1's right there, which is WL cubed over 6. So it's equal to 1 over EI positive WL cubed over 6, or WL cubed over 6 EI. All right, now I'm going to go get the little equations that I was looking for, and I'm going to try to drop them in right over here. Be right back. Okay, so look at our solution for delta at 0 equals, there's a 1/4 there, and maybe I have to move this just a little bit out of the way. There's a 4th there, so it's minus WL to the 4th over 8EI. That's the deflection. Now, is this situation what they're calling case 2? Is that what we're dealing with? Well, not exactly. Ours is backwards. But would our deflection be the same? Yeah, it would be the same, whether you were going from the right to the left or the left to the right. If you've got a load of W and then a length, their maximum deflection, again, that's delta, is minus WL to the 4th over 8EI. Look at that. Look at that. All right. Now, theta. Let's look at theta. Our theta, WL cubed over 6EI. And look at theirs. Oh, wait, we got a sign in there. We got a sign change in there. Why are we wrong? Why did we have a sign error? Well, if you look at, and we have to zoom in really, really tight, this angle that they've got is negative, that it's going down, right? But if you look at our problem, we're coming from the other side, and we would be going up. Okay, my sides are wrong because I think my camera image is inverted, but so this is good. This is good. This gets us, that's got us what we need. That sign error is because we're looking at it from the other side, and so that's okay. So we got both of those correct. Now, it would be hard for us to have gotten both of those correct and not gotten our general equation right. Well, they actually give us the general equation here. Delta equals minus WX squared over 24EI. And I have, well, they pulled a WX squared out of all of those terms. Can you see that? Each one of these terms in here has a WX squared. So if I put that out front, a WX squared, then and they put the negative out there too. So that negative goes away, and that becomes a negative, and that goes away. And they have an x squared. They pulled out a 24. Well, 4 over 24, well, that'd be 1/6, and 6, that would be 6/24 is 1/8. We got the same numbers. We got the same thing. So what they have, this whole thing in the back of the book, they've got this whole chart that gives me a whole list of these particular solutions I'm able to do. I can go through and calculate those for you, or you could calculate them for me. Maybe that's a better solution. I like that better for some reason. We can calculate those. And so that's where this is kind of, to me, this is kind of fun. I mean, the first time I look at these equations like this, and I go, oh, wow, where'd those come from? Wow, that's amazing. They're in the back of the book. Those must be special. They're not. There's stuff that we're fully capable of doing as engineers. We've got the math skills. We've got the knowledge. We've got it. And so I want you to start thinking about that with respect to other equations and other things that you find in the backs of books. They're not beyond you. You just have to apply yourself. And then maybe there's a trick or two that we've got to learn. And we've learned a lot, but these are simply partial differential equations with boundary conditions. And we did that a couple years ago in our math class, or a year ago. So, all right. I hope you're doing well. I want to do another example, so I'll go on and do example 8.3. That'll have to wait a little while because I'm due in a CAD class right now. But don't worry, there's more to come.